Welcome to our MEM360 workshop project. In this video, we will present the fabrication of the turbine blade, a hands-on project designed to strengthen our practical skills in manufacturing processes. This is the table of the contents for this video. Let us begin by introducing the group members. First, we have me, Hana Najwa binti Muhammad Azlin. The second members, we have Muhammad Amirul bin Shamsul Baharim. The third member, we have Muhammad Afiq Firdaus bin Hairul Anwar. And lastly, we have Muhammad Hasbullah bin Hamzah. This is the work distribution for each members. In this project, each group member is assigned to present a specific section of the video. Hana is responsible for explaining the safety equipment and techniques. Amirul handles the improvement discussion parts, suggesting the ways for the process that can be improved. Afiq discusses the problems faced during the project along with the solutions implemented. Lastly, Hasbullah presents the manufacturing step process, covering each stage in detail. The MEM360 Turbine Blade project aims to enhance students' practical understanding of manufacturing processes through the hands-on fabrication of a turbine blade. This project involves key workshop operations such as cutting, milling, drilling, lathe machining, welding, grinding, and surface finishing. Students are required to plan the process flow, allocate tasks, and ensure precision in execution. A video presentation is also prepared to showcase safety practices, detailed process steps, encountered problems with solutions, and suggested improvements. This project not only develops technical and analytical skills but also promotes teamwork, safety awareness, and real-world engineering application. Before entering any workshop, you need to scan the QR code for workshop entry and usage logbook. Before beginning any fabrication process, safety is our top priority in a workshop environment. Each group member is required to wear proper personal protective equipment or PPE and follow strict safety procedures. We start with safety jacket. Safety jacket provides a protective layer against sparks, metal chips, and dirt, especially during grinding, cutting, and welding tasks. Next is safety shoes. Safety shoes protect the feet from impact injuries caused by falling tools, metal parts, or heavy equipment. Let's move on to the next safety equipment, which is the safety goggles. Safety goggles protect eyes from flying chips, dust, and sparks during milling, drilling, and grinding. Prevent injuries from sharp fragments or debris. Next, we have safety gloves. Safety gloves protect hands from sharp edges and high heat, allowing safe handling of hot or rough materials during cutting and grinding. For welding process, we have extra safety equipment. First, we have welding helmet, which protects the eyes and face from UV or IR rays, bright flashes, sparks, and molten metal during welding. Next, we have heat-resistant gloves, which it protects hand from sparks, sharp edges, and high heat during welding, allowing safe handling of hot metal parts. For every workshop, safety jackets and safety shoes need to be worn. This shows the proper attire for workshop.
Before starting any machine, it's critical to measure and mark all parts accurately. We use a vernier caliper to check the thickness and the width.
For cutting process, before operating the handsaw, we inspect the blade for any damage and ensure the guard is properly adjusted. Materials are held firmly using a clamp to avoid hand contact with the blade. We maintain a safe distance from the cutting zone and keep hands clear at all times.
Cutting process. We begin to fabricate the part for the blade. We cut into 3 pieces based on the requirement dimension, which is the width of the blade is 70 mm, the height is 24 mm, and the thickness is 6 mm. For the drill point, we use the center punch to ensure the drill bit stay on target.
During drilling, we ensure the material is firmly fixed using clamps to prevent spinning. The correct drill bit and speed setting are selected to avoid tool breakage, and we never apply excessive force on the drill feed to avoid it from breaking.
Drilling process. We drill several holes based on the design. The first one, we drill center hole with the radius 8 mm on part 2 and part 3. Second, 4 mm holes on part 2. Last, the 3 mm holes on part 3. All holes were made using the drill press with a proper clamp.
When using the milling machine, the workpiece is properly clamped with a vise to prevent movement. We check that the cutting tool is sharp and correctly aligned. Hands are kept away from the cutter, and the machine is stopped before any adjustments are made.
Milling process. We use the milling machine to cut the flat surface of 3 mm depth on both part 2 and part 3. This surface ensures a proper fit and alignment during a final assembly. We then perform a true cut on part 3 to create the blade opening. We use a 6 mm diameter end milling.
For the lid, we make sure the workpiece is tightly secured in the chuck and the chuck key is removed before starting. We avoid wearing gloves and loose clothing to prevent entanglement, and we never touch the rotating part while the machine is running.
Turning process. Using the lathe machine to change the profile of part 2 and part 3. We begin to change the outer radius 27.5 mm, and then we machine part 1, which is the central shaft that fit into the center hole. Part 1 was turned to a diameter of 6 mm and the length of about 14 mm. During the handle the machine, always keep our hand clear of the rotating part.
For welding, we always wear a welding helmet and heat-resistant gloves.
In this step, we assemble all parts, which is part 1, the shaft, part 2 and part 3, the blade section, and the part 4, the blade. We use the small shielded metal arch welding machine to perform a spot welding at the joint. We use the appropriate welding rod and set the correct current based on the material thickness. Threading and countersink. First, on the part 2, we drill a countersink to fit the head of an M4 flathead screw. Last, on the part 3, we use the SKCM4 hand tab to create a thread. The file to manually remove any small burrs, sharp edge and imperfection in tight areas.
While grinding, we wear safety goggles to protect eyes from sparks and flying particles. We avoid pressing too hard on the wheel and allow the grinder to operate at its proper speed to prevent breakage.
Grinding and polishing. After welding, we use a grinder to remove the weld bit and improve the surface finish.
Okay, next. Problem appear and solution in process. I I would like to share with you guys 5 main problems that we face during the manufacturing process of a turbine blade in the workshop, along with the solution and lesson we learn from each situation. The first problem was that the machine and equipment were not sufficient in the workshop. Since many students had to share the same machine, our process becomes slow. Our solution was to divide into 2 groups. One group wait for their turn, while the other carry out another process. This helped reduce idle time and keep the work going. The second problem was the screw hole were not drilled in parallel. This made it difficult to assemble the parts. We solved this by slightly enlarging the screw hole to make the misalignment less visible and allow proper fitting. However, we realized this may weaken the joint, and we learned the importance of using a jig or guide during drilling. The third problem was the shaft diameter was not equal on both sides. This caused difficulty when fitting the shaft into the support plate. Our solution was to grind the thicker side slightly to make it fit. We understood the turning machine need to be properly calibrated to ensure consistent diameter. Okay, the next problem was the blade length was too short because we followed the given drawing without checking. To solve this, we shortened the shaft by 3 mm to balance the total length of the assembly. This taught us that we should always verify technical drawings before cutting materials. The last problem was difficulty in setting the correct current on the welding machine. Many team members were unsure about the suitable welding settings, so we tested the welding current on the scalp plate first before welding the actual blade. This helped us avoid defect and ensure a clean and strong weld. For the conclusion, each problem gives us a valuable learning experience, from planning and accuracy to selecting the right process parameters. We also realize how small mistake can have a big impact on the final product quality.
Before we start any machining or fabrication process, it's important to create a digital design using CAD software like SolidWorks, AutoCAD or Fusion 360. This gives us a precision and detailed model of the product we want to make. Then we use CAM tool to simulate the machine will cut, drill or melt the part. This simulation helps us spot error in tool paths, detect collision and optimize the process before doing it for real. Trial cut and measurement is an important step before doing the actual machining. First, we make a light cut on the material to test if our setup is correctly. Then, we measure the result using a protractor or caliper to check the angle or dimension. If the cut is not accurate, we adjust the tool position, angle or machine setting. This process helps us avoid wasting material and ensure the final part meets the design specification. Before we start working on the actual part, it's a good idea to use scrap material for a trial run. This lets us test if the machine setup, tool alignment and cut condition are correct. It's especially helpful for students to build confidence and fix any issue early. By doing this, we reduce the risk of damaging the real workpiece and avoid wasting material.